Having now taken a look at some specific numerical techniques and having taken a very deep dive into the very specific perturbing forces generated by n perturbing masses, let's zoom all the way out and look at a very, very general treatment of perturbations on our orbital elements. And we're going to start with something known as variation of parameters. We're going to look at two quantities that are normally conserved in the unperturbed two-body system, the specific angular momentum and the eccentricity vector, and we're going to try to figure out how they evolve in the presence of perturbing specific forces, F. We start with the specific angular momentum, which is given by the cross product of the orbital radius vector with the orbital velocity vector, and we will differentiate it in time in the presence of a specific perturbing force, F. That is, the inertial derivative of the specific angular momentum is equal to the product rule, the inertial derivative of the orbital radius crossed with the velocity, plus the radius crossed with the derivative of the velocity. The derivative of the radius is the velocity. Velocity crossed with itself is 0, so this term goes to 0. And ordinarily, this term would also go away because we would get, by our two-body equation of motion, a vector that is proportional to r. However, now we have the derivative of the velocity is negative mu over norm r cubed r plus this specific perturbing force. So the cross product of the first part still goes to 0. Let's write this out. So distributing the cross product, the first term still goes to 0, but we are left with an r cross f term. So very unsurprisingly, the derivative of the specific angular momentum looks a lot like a specific moment, or a position vector crossed with a specific force. We're going to do the same thing for the eccentricity vector, which we've previously found was equal to v cross h over the gravitational parameter minus the unit direction of r. The derivative of the eccentricity vector is 1 over mu times the product rule applied to that first cross product. So the derivative of the velocity crossed with h plus the velocity crossed with the derivative of h minus the derivative of the unit direction of the orbital radius vector. This term becomes negative mu over norm r cubed in the r direction plus f crossed with h. And this term becomes the vector triple product v cross with quantity r cross f from our previous result for the derivative of h. Rewriting this and cleaning it up, we have 1 over mu times the quantity f cross h plus v cross quantity r cross f minus the inertial derivative of r over r plus r cross h over r cubed. Applying the quotient rule to this term, we get negative r dot over norm r squared in the r direction plus 1 over r in the v direction. And this term over here is 1 over norm r cubed times another vector triple cross product of r cross v. This triple cross product works out to r dot v in the r direction minus r dot r in the v direction. So this entire term can be rewritten as 1 over r cubed r times r dot in the r direction minus r squared in the v direction, where we've used a previous result that r dot v is equal to r dot. This term exactly cancels this term, and this term exactly cancels this term. And so this entire term over here is 0. And therefore, the derivative of the eccentricity vector is just this, as shown here. We could also substitute here for the specific angular momentum, the quantity r cross v, and then evaluate both of the resulting triple cross products. And that would give us that is a term of f dot v in the r direction minus f dot r in the v direction, and here v dot f in the r direction minus v dot r in the f direction. And so we can combine many of these terms and get That is, the derivative of the eccentricity vector is 1 over mu times the quantity 2 v dot f in the r direction minus f dot r in the v direction minus v dot r in the f direction. We can also apply now various geometric relationships for R and V, but honestly, this is not hugely illuminating. And most of the time, you will see the derivative of E given in just this form. Let's zoom out for a second and think big picture. Remember that your orbit is entirely given for all time, if it's a pure unperturbed two-body orbit, by just the position vector and the velocity vector. The fact that we now have the ability to calculate the time derivatives of these two previously conserved quantities, h and e, means that we can say what our osculating orbit looks like for all time. But these expressions are not hugely intuitive. They don't give us a really good sense of what is happening with the orbit. It would be really great if we could instead find differential equations in time for the orbital elements of our perturbed orbit. And we can by deriving what are known as Gauss's perturbation equations.